right. Let's pick back up. Let's see. Still talking through topic 1 notes. We'll finish those today. So we'll finish the topic 1 notes and say some more in R. We'll look at the pottery data that we started Wednesday, and I'll show you another data set also. Okay. So we started talking about how we're going to represent our multivariate data mathematically. Capital X, we said, is a matrix of numbers. So suppose we have n individuals and p numerical variables. Then we could organize our entire data set in a matrix, call it capital X, n by p. In terms of characterizing our data, the individual variables themselves as well as joint relationships. Some key ways of doing that are here. We're interested in typical values, which we could also say describes the location of a variable. Where does it tend to be? Also, how spread out does it tend to be? What's its variance? And in terms of joint relationships, we can speak about correlations. And remember, we said that correlation is a measure of linear association. So when we have two numerical variables that we suspect are linearly associated, then correlation is a natural way to quantify just how much they are associated. Correlation, a number between -1 and 1 that speaks to strength of linear association. To estimate location, we're going to use a sample average, typically. There's different ways to define location. We could talk about a mean or a median, or a trimmed mean or something else. But we're going to generally, unless we specify otherwise, be thinking in terms of means. So to estimate location for a variable k, we'll use the sample average. Add up all the observations for variable k and divide by n. To quantify variance, we'll use the usual variance definition. Sample variance of variable k, also called S sub kk, is an average squared difference of variable k from its mean. And remember, if it's really spread out, that number is going to be big. You're going to have lots of big differences, which when you square them become even bigger, and you average them up, you get a big number. Variance tells us about spread. That's the variance, and a standard deviation is just the square root of a variance. So if s squared k, same thing as skk, is the variance of variable k, then the square root of those things is its standard deviation. The nice thing about standard deviation is that it's on the units of the original data. So if the data are in inches, then the standard deviation is in inches. Variances are squared quantities, so their units are squared units. Standard deviations are a little nicer for that reason. And then covariance and correlation, we defined last time. Covariance is a number between -infinity and infinity that quantifies strength of linear association. And correlation is a standardized version of the covariance. SIK is the covariance, sample covariance, between variables I and k. If you divide that quantity by the product of the two standard deviations, you standardize that number to be between -1 and 1. That's what a correlation is. When we have our data, capital X, n by p data matrix, we're going to represent all the variances and covariances in a matrix. If I have p variables, then there are p variances. S11 would be the sample variance for variable 1. S22 is that for variable 2, and so on. So the diagonals of this thing that we're calling S sub n contains the sample variances of all the variables. And then the off diagonals contain covariances. For example, this element here in row 1, column 2, S12, is the sample covariance between variable 1 and variable 2. A lot of what we're going to do this semester begins with this, Sn, or this, which is just a standardized version of S. Capital R is, whereas capital S is called the sample variance / covariance matrix, what's below capital R is called the sample correlation matrix. So these entries in R are the same entries from S where we've divided by the product of standard deviations. So for example, R12 is S12 divided by the square root of S11 times the square root of S22. So this is the correlation between variables 1 and 2. There are 1s down the diagonal because when you take that covariance and divide by the square root of that twice, you get back 1. Every variable is perfectly correlated with itself. If you drew a picture of variable 1, a scatter plot of variable 1 against variable 1, it'd be a straight line, and that's correlation 1. So a correlation matrix will always have 1s down the diagonal, and the off diagonals are the correlations. One more thing on this slide here. Covariances, correlations have a nice feature to them in that they are standardized. They are standardized. So suppose we have some of our p variables are much more variable than some of the other ones. Maybe we have variable 1 is like percent contaminants in a device, a number between 0 and 1. And variable 2 is total sales for fiscal year 2014 or something, and that's a number thousands. Then the variances between those two will be very different. And a lot of the multivariate techniques will be drowned out, will be completely driven by the really variable ones. And in particular, that one that lives between 0 and 1 will essentially be left out of the calculations because it contributes so little, relatively speaking. But when you standardize and change your starting point from S to R, it fixes that issue. By standardizing and going to correlations, every variable is on equal footing. So we'll see that in practice. When you have a data set, you will often need to make a decision, should I standardize or not? And typically, you'll want to standardize when you have that issue like I was describing. Some variables are much more variable than others. Both of these are matrices. They are square matrices. Topic 2, when we get to that next week, we'll go through the basics of linear algebra that you need. So we'll revisit the idea of matrix and square matrices. But these are square, which means same number of rows as columns. And they're also symmetric. The correlation between variable 1 and variable 2 is the same thing as the correlation between variable 2 and variable 1. All right. There were these data that we were playing with last time on chemical compositions of 26 Pottery samples. This is pottery.r. It's on eCampus. And let's come back here and play with these data a little bit more. So we have 26 observations, and each of these samples came from one of 4 sites. So site is a categorical variable that takes values L, C, I, or A to designate which site the pot came from. And then we have 5 numerical variables that are the percentages of these different chemicals. All right. So here's code you can use to read in the data. I'm going to read.delim in this case. We're going to see read.csv and read.delim. There's a couple of different functions that we often use to bring data in to R. So let's read these in. Remember that these next 3 lines of code, the dim tells you how many rows, how many columns. So it tells you how big is your data. Head shows you the first 6 rows. So it's just a quick peek at what the raw data look like, rather than trying to print the entire data set to screen. And summary tells you a simple summary of every column. If it's a categorical variable in a column, it tabulates how many times were each of the different values taken. If it's a numerical variable, then it gives you numerical summaries. Let's run this over in R. Prior to running what I just ran, you want to make sure that R is pointing in the right place, remember. When you say read.delim or read.csv, you're going to give it a file name in quotation marks, and it needs to be able to tell where that file is. We have already set up our working directory to be in the right place. Remember that you can do this point and click style. Windows machine, go to File, Change Directory. Mac, go to Miscellaneous, Change Directory. If you try to read in a data set and it throws an error, could not establish connection or something like that, it's because it's not pointing in the right place. All right, here's our data, the first 6 rows. Here's the summary. So here's like mean of aluminum and mean of iron and so on. Here are our site variables. We had 14 pots from site L, 5 from I, 2 from C, 5 from A. To illustrate a couple of calculations from the notes, let's pull out a subset of these already simple data. This is the first 4 rows and just the 4th and 5th columns. So 1, 2, 3, 4, and 5. We're going to pull out calcium and sodium only, and the first 4 rows only. That's what this is doing. Remember, square brackets are what you use to subset a vector or an array in R. A 2-dimensional array, like DTA, like data, to use square brackets, you need to tell it something about the rows that you want and the columns that you want. 1:4 is saying rows 1, 2, 3, and 4. Comma says, and then here's the columns I want. So what rows do I want? Comma, what columns do I want? So I'm going to run this. Now we have this tiny little data set. N is 4, P is 2. Back in the notes, we defined sample average. Sample average is add up all the values for a variable, divide by the number of values. The sample mean for what is now variable 1, calcium, the sample mean for variable 1 would be add up those 4 numbers for variable 1. So data toy, the 4 numbers for variable 1 are these, 0.15, 0.12, 0.13, 0.16. So I have 0.15 plus 0.12, 13, 16. Add them up, divide by 4. The sample mean for variable 1 is 0.14. Similarly, we have a sample mean for variable 2. And then we're going to say that x bar boldface is a vector. So x bar, the vector, contains all the x bars for our individual variables. X bar is, in this case then, a 2 by 1 vector, a 2 vector, column vector. It contains two things. The first is x bar 1, the second is x bar 2. Back in R, here's some example R code that you can start playing with. Let's compute x bar. And I'm going to show you multiple ways to do the same thing. If you do this concatenate function is a generic way to string together multiple things. Suppose I want the vector that contains the number 1, the number 0, and the number 10. I can do that by concatenate the number 1, the number 0, the number 10. That's now a vector to R. So back here, I'm going to concatenate the average for variable 1, comma, the average for variable 2. So x bar is going to be the vector of length 2. One way to do that is to simply add up column 1 and divide by n. The sum function does that for you. And then add up column 2 and divide that by n. That's one way to do it. Another way to do it would just be to use the mean function. There's a built-in mean function. So here's mean of column 1 and mean of column 2. Yet another way to do it would be to say, I have a data frame. That's an array with rows and columns. The apply function allows you to apply some function row by row or column by column, whichever you want. If you say apply to my data frame, and if I say either 1 or 2 here, that's my choices. Look at question mark apply for the help file. If you say 1, then it's going to apply the function you specify row by row. By saying 2, it's going to apply it column by column. We have a 4 by 2 data set, and we're currently trying to compute the groups or the variable specific means. That's the same thing as the column means. I want the column means. So apply to this array, column by column, the function mean. Yet another way to do it is to use the built-in function call means. There's a call means function, there's a row means function. And using vector arithmetic, I'll let you play with that one later. We may see this type of syntax later, but you've already got 4 ways to do it, so you're good. X bar, let's just pick any one of these. They'll all be the same. Those are the numbers from the slides, 0.14, 0.255. We can also match variances and covariances. I won't go through this in detail, but you've got it there if you want to read through. S11 would be the sample variance of variable 1. So I've got code here that does the same. One technical issue that I've mentioned once before in our class is that the way we're defining sample variances right now looks different from what you're used to seeing probably. Remember that usually in Stat 101 we would define a sample variance as add up these squared deviations and divide by n minus 1. We haven't done that yet. We'll get to that eventually. But we're currently dividing by n. So the sample variance for variable 1 would be add up individual value, this is the first value, 0.15, minus the mean for variable 1, and square it, plus the second value, which was 0.12, minus the mean squared, and so on. add up those squared deviations, and divide by the sample size. Same thing for variable 2. And then here are covariance calculations. Add up, instead of squared deviations, you add up a product of deviations between the two variables. So x1 minus its mean times x2 minus its mean. Here's code that you can use. What I'm doing right here is first setting up an empty container to hold all the variances and covariances. I'm making a capital S sub n. That's what we called the sample covariance matrix back in the slides. It's a square symmetric matrix. In this case, with p equal 2, it's a 2 by 2 matrix. Two variables, so I have two covariances, or I have two variances, and one covariance that goes in the off diagonal. So let's set up an empty one. When I do this, Sn is a 2 by 2 array, but it doesn't have any numbers in it yet. So here are numbers that we could compute. The first row, first column. S sub n square brackets, 1 comma 1, means first row, first column. This needs to be the sample variance of variable 1. Variable 1, if we look right here, variable 1 is calcium. One way I can access that column is to say data toy $ calcium. There's multiple ways to do it. Another way would be to say data toy first row. Same thing as data toy calcium. In the script, I'm going to take data toy calcium, those 4 numbers for calcium, and subtract off the sample mean for the first variable for calcium. Notice that there's 4 numbers right there, but x bar 1 is just one number. In R, let's make a quick little vector, sample 1 to 10. So x is a vector of length 10. If I take x and I say subtract off the number 1, it does component by component subtraction. So when I take a vector and say multiply by a constant or add a constant or subtract a constant or divide by a constant, it does that one by one. So this is going to give me the difference for each of the 4 pots, observed calcium concentration minus the mean for calcium. So this highlighted region here then will give me 4 numbers. I want to square those 4 numbers, and then I want to add them up and divide by n. That's the sample variance for the calcium variable. Similarly for the sodium variable. And then covariances are like average products. So the sum of the product of calcium minus its mean with sodium minus its mean. Add that up, divide by n. Here is what we get. Sn, sample covariance matrix. The variances are on the diagonal, and the covariances are in the off diagonals. Back in the notes, S11 was 0.00025, S22 was here, and S12 was there. Covariance matrix. Another way to do all those calculations in one fell swoop, this is the way we would do it going forward. We could use the var function. Var on a vector gives you a single variance calculation. But var on an array, an n by p array, it's assuming you have multivariate data like we have. individuals in the rows, variables in the columns. So when I say var of an n by p matrix, it's going to give me a p by p covariance matrix. The var function in R will do the variance calculation like you saw it originally. Add up the squared deviations and divide by n minus 1. In order to match what's in the slides, I'm going to do that, but I divided by the wrong number for our purposes. So I'm going to undivide by that wrong number and then divide by the number I wanted to divide by. So this is a one-line way to match our calculations. Same thing. Here are manual calculations for the sample correlation matrix as well. Easier way to do sample correlation is with the core function. So you could follow the code that's up above. That shows you exactly what a correlation is. In practice, just like in practice, we would probably use the var function with a real data set. We could just use the core function with a real data set to compute R. That's the correlation matrix. Every correlation matrix has ones down the diagonals because every variable is perfectly correlated with itself. So what we really care about is what's in the off diagonals, the correlations. Okay. If you haven't already seen this slide, you have the R cookbook, which is a good resource for getting up to speed. On the CRAN website, if you search Google for CRAN R, it'll take you here. And over on the left, there's a manuals link. And the introduction to R manual, I think, is pretty good. If you want to go further in R, some of these other manuals are very helpful. Like with R, if you have big data sets, sometimes R will get bogged down with a really big data set. Sometimes you can write computationally intensive stuff in, say, C. Use R to manage your data, but for the really tedious, intensive, like loop calculations, you can sometimes do a lot better by shipping it off to C. And it's pretty easy to work with C or other programming languages through R. There's a built-in interface where you load in the data to R and then you .c it out to C. And it can make your programs go orders of magnitude faster. Okay. Let's see a couple of pictures. We'll see several pictures throughout the semester for visualizing data, multivariate data in particular. So let's make our first picture with the Pottery data. A simple way to visualize your data, if you read in a data set, I recommend doing these things initially, and then maybe the next thing to try is a pairs plot. If I say pairs of my data frame, what I get is all pairwise scatter plots. So for example, this plot right here is all the aluminum concentrations plotted against the iron concentrations. Here's aluminum versus magnesium, and so on. Is that magnesium or manganese? Okay, good. So one picture shows you a pretty big picture summary of all the joint relationships. And you would look through these pictures and ask, what do I see? Here, for example, is what appears to be maybe a negative association. As calcium increases, it appears that aluminum tends to decrease. Here's what appears to be a positive relationship. As magnesium increases, iron appears to increase. Although, something interesting is that there's this big gap. There were a lot of really low magnesium values, like really low magnesium values, and for those, iron tended to be kind of low as well, but it spread a lot more than the magnesiums did. And then there's a different group. There's like a separate cluster of values over here for which magnesium was substantial and iron was substantial. You could look at pictures like these for rough patterns. Do I see relationships or do I not see anything? If you have points that are just completely randomly bobbing around with each other, maybe in a spherical pattern, that would say there's not much of a relationship between those variables. You could also be looking at pictures like these for potential outliers. So if this was the picture of aluminum with iron, and all the points were way over in the bottom left corner, say, and then there was 1 or 2 points way up in the top right corner, that's outlier kind of evidence. So that's indicative of there's at least one individual in your data set that looks substantially different from the others. Over on the far right, one of our variables was really not a variable so much as just a class membership or a category variable. Site is categorical. R still tries to make scatterplots. If you say pairs, it will make scatterplots of everything, even if it's a categorical variable. But you need to understand that this is not really a plot of numbers. Site takes the values, I forgot what they were, but it's coded them into just numbers. Site 1, Site 2, 3, and 4. But these aren't really numbers. These are just placeholders for the different categories. It still can be an interesting or informative picture. For example, if we look at aluminum versus site, you can see that the aluminum values at Site 1 and those at Site 3 tended to be higher than those at Site 2 or Site 4. For iron, it was the other way around. It tended to be low at Sites 1 and 3, higher at Sites 2 and 4. And this ends up being interesting in the context of these data, by the way, because these different sites correspond to different time periods. And if you can take chemical compositions of them, you can hope to date the sites. Maybe I know that site X is from a particular time period. Then here's a new site. We don't know what time period it's from. Suppose the concentrations of its pottery is similar to the one from over here. You can maybe make inference about dates. So pairwise scatter plots are one way to get a big picture view of the data. Obviously, that will be challenging if you have lots and lots of variables. We only had 6 columns in our data set. Suppose we had 100. Then this picture would be too detailed to view. Be too much stuff on it. So think of pairs as particularly useful with smaller data sets. I'll just mention another plot type. This is called a coplot, and I'll show you how to make it in a second, but what it's doing is doing scatter plots by the level of a categorical variable. In our case, we have we have multiple chemicals, and we might want to look at, say, calcium versus sodium, but we might want to do that by site. Let's look at calcium versus sodium at site I. Let's look at calcium versus sodium at site L, and so on. So there's a simple function call in R that allows you to make a picture like this. Here are the commands for doing that. Pairs is simply pairs of a data frame. Coplot, there's a function called coplot. And the syntax is, I want to make scatter plots of calcium versus sodium. So calcium tilde sodium is the syntax it wants. And then a vertical bar to say by, or like condition on sort of site. Let me show you I'm not sure I want to show this. Here's another data set. You can get it from a package in R. Yeah, I want to say this. Let's see. Let me go back to our scripts. mtcars.r is another script from eCampus, and shows how to make another couple of pictures. So there's 3D scatter plots that you can make. This is for cars. I'll show you the data in a second. But we have a variable for the weight of the car. We have a variable for miles per gallon of the car. And we have a variable for the displacement of the engine. How big is the engine? So with 3 variables, we could try to make a 3-dimensional scatter plot. And there are functions in R for doing that. So here's a plot of all the cars in this data set that we'll look at in a second here. 32 cars. In terms of these 3 variables, here's a 3-dimensional picture. And you can color code the points even. So here are these green points. I manually color coded them to correspond to all the 4-cylinder engines. And the blue points, I color coded them to correspond to the 6-cylinder engines, and then here's the 8-cylinder engines. You can also make 3D plots like this that are interactive in R, that you could click on and spin around and stuff. Those are nice. Okay, I'll just let you look at the code on your own. We may come back to this and do some 3D plotting later in this semester, but for now I'll just point you to here's a plot that makes that 3D scatter plot, and here is a plot that makes an interactive 3D scatter plot. So if you do this, you can click it and rotate it and see the data from different angles. Okay, I'm going to skip past these things because I want to talk about what's at the end of these notes. Topic 1 on distance. Much of what we do in multivariate has to do with distances. For example, when we do cluster analysis, when we want to group together our individuals in our data set such that within groups they're more similar than between groups. That similarity idea, we're going to tend to quantify that with distances. So Euclidean distance is one way to compute a distance. You have 10 numbers of variable 1 and 10 numbers of variable 2. You could compute a distance between those by component-wise differences squared, add them up, take the square root. That's Euclidean distance. In statistics, we're going to want to modify that Euclidean style of distance a little bit. Let me show you why. Here's a review of Euclidean distance. Suppose we have 2 points in p dimensions. Let's say p is the first one, and we'll let O be the second one, and we're going to put the second one at the origin. So this is p-dimensional space. 2 dimensions is easy to see, 3 is harder to see. We're in arbitrary dimensional space right now. We have 2 points in that space. The distance between the 2 points, Euclidean style, straight line style, is x1 minus the component 1 for this guy squared, plus x2 minus the component here squared, plus ... Add up all the squared differences and take the square root. And it turns out then that all the points that are a constant distance, say c squared, from the origin, can be described with this equation. Whenever x1 squared plus x2 squared plus ... xp squared equals c squared, you are c squared from the origin. So if you considered all values of x1, x2, xp that satisfy this, you're going to have a sphere centered around the origin, called a hypersphere if p is bigger than 2. And if p is 2, it is a circle. So Euclidean distance is weighting every variable the same in computing these squared deviations. Let me show you with a picture why we need to modify this. Here's a picture of two variables against each other, x1 on the horizontal axis, x2 on the vertical. x1 has more variability to it than does x2. x1 is spread out further on the horizontal axis than x2 is on the vertical axis. So consider these two blue points. Blue point, blue point. Both of these points are equidistant from the origin. This blue point is at x1 equals 0, x2 equal 2. And this point is at x1 equal 2, x2 equals 0. So in terms of Euclidean distance, any point on this circle has the same distance to the origin. But taking in terms of data, this variable is more variable than that one. And that means that this point right here is less unusual than this one. This point is more unusual than that one. It's further away from where its values tend to be than this one is from where its values tend to be. It has to do with the variance. Because this is more variable, this point is not as unusual as this one would be. This one's further out in the tails relative to the x2 values than this one is for x1. So the reason I'm saying this is a Euclidean distance is not ideal in this case. I wouldn't really want to call those 2 points equidistant. So statistical distance is going to incorporate variances. And eventually it's also going to incorporate covariances. So here's a modification of Euclidean distance. Instead of saying the distance from point P to the origin is the square root of x1 squared plus x2 squared, we're going to weight each of these variables by their variances. Since x1 is more variable than x2, we're going to divide by a bigger number for x1 than we are for x2, which means we're going to downweight x1. Less variable variables for which we have more confidence, will get upweighted relative to those that are more variable. And now we have a different relationship for points that are a constant distance from the origin. It's squared components, but now divided by constants. That turns this into an ellipse instead of a circle. So here's the same data, but I've used a different definition of distance. It's a statistical distance, and now, according to the statistical distance, the ellipse, the 2 points are equidistant from the origin. So as we go forward, we're going to be seeing statistical distance a lot. And it harkens to this right here. I'll fill in more details as we go, but the idea is we're going to weight the different variables according to their variability. We're also going to allow for correlation. So let me go here. If I weight by the variances, I handle this non-constant variance issue. But what if the variables are correlated? Here's like the same data, but if they've been rotated, because there's correlation between x1 and x2. As x1 increases, x2 tends to increase also. There was no correlation here. x2 doesn't care what x1 is doing. So if there is correlation, what does that do to the way that we compute distances? Here's the original ellipse. But it's not capturing the essence of the actual data. So without beleaguering this, what we do is that statistical distance that we were looking at, that's dividing the variables by their variances. Now we're going to rotate the whole picture. So if I rotate the axes by some appropriate angle theta, then my ellipse, if I draw it according to those axes, it can fit a correlated data set. So don't worry if this is not 100% clear. I'm trying to give mostly conceptual motivation right now. What we end up with is a distance calculation that looks like what we had before. It's variables weighted by variances, but now there's this cross product term in the calculation. The cross product term is how we get that rotation. Okay. Okay, I think that's good enough for topic 1. Topic 2 is coming, and you might get started looking through it this weekend. I'm going to post our homework assignment, our first homework assignment this weekend. Topic probably Sunday night, next Sunday night, not this week. You'll have all next week to work on it. So topic 2 is going to go through the basics of vectors and matrices. Okay. So topic 2 is a little bit more math. This class is when I teach this class, we have to spend a little bit of time up front, I think, doing foundational stuff. So multivariate statistics, I think the first lecture, it can be easy to do it. Click a button to do principal components, say. It's not as easy to understand what you're doing. And my goal with you all is to help you understand what it's doing. In order to do that, you do need to understand some of the math underneath it, and that's where topic 2 comes in. Topic 2 will be the linear algebra. Topic 3 will do some probability stuff, and as soon as we can, we'll start getting into real data sets. But a little bit of background in the first week or 2, and then we'll get to the fun stuff, clustering, principal components, and all that. All right, any questions right now? Okay, then I will see you Monday.